surface transport of fluids, which includes tsunami and stuff.
Thank you for giving me this opportunity to come back here again and give this talk. So I'll be talking about surface transport in finite lumps of stationary relativistic fluid. This work is based on this following work, which is uploaded in the archive and was done in collaboration with J. Armas, who is in Brussels, postdoc at Brussels, and Jyotirmoy Bhattacharya, who is at Durham. And I will also talk about some ongoing work at the end, which includes Felix Hale, who is a student at Durham. So, hydrodynamics is a tractable, effective framework to study the low energy near equilibrium states in any finite temperature system. The description of these states, these near equilibrium states, in terms of the microscopic degrees of freedom may be very complicated. But nevertheless, the effective theory that by which I mean the hydrodynamic theory, is constructed purely on the basis of symmetries inherent to the microscopic theory and also with fewer effective degrees of freedom. The information of the underlying field theory, the underlying UV theory or the microscopic theory, is encoded in a phenomenological way in the transport coefficients that characterize the effective macroscopic descriptions. In recent studies, inspired by ATS safety correspondence and its connections to black hole physics and all, has valuably contributed to the improved understanding of the structural features of the subject, which is led by Siraz and his group and other groups also, and has led to the unraveling of new transport phenomena. But most of these latest developments mainly focus on the description of those low energy states, near equilibrium states, which are in a phase of the fluid which fills the entire space-time. In other words, the hydrodynamics that has been explored in most of these recent developments is the effective theory of a class of states which does not involve any fluid surface or a phase boundary. And the aim of this work is to analyze the situation where the class of states described by the effective theory of hydrodynamics is extended to incorporate those states which include a fluid surface and which separates two phases of the fluid. And in other words, we are focusing on finite lumps of relativistic fluids which occupies only a finite subspace of an otherwise non-compact spacetime. And one concrete example of our setup, I mean, we have this setup in our mind, but our analysis is more general than that. But one concrete example is a large N field theory, like n equal to 4 super Young mills in d equal to 4 dimensions, where these metastable finite lumps of deconfined phase is separated from the confined phase by a phase boundary.
So you're going to talk about global ADS then, is that right?
Yeah. And if we like have to address issues regarding that, like in the context of ADS.
So it's on S3.
I see. But sorry, I should know this whole story better, but why couldn't you have a lump of deconfined matter in a otherwise confined phase even in R3? And then presumably that lumps will evolve, I mean, if there are pressure differences inside and outside, etc., etc. At least physically it's a sensible thing.
Yeah, physically it's a sensible thing, but for this work we are considering to like stationary fluids.
I see, I see.
Stationary.
So that is quite unusual. I imagine you only at when you're at the cusp of a phase transition or something, then you can have two equally states. That's the kind of situation. Oh, I see. Okay, thank you.
Is that right?
Is it wrong?
Wait, there's no fine tuning here, right? It's just
I see.
You throw in lots of stuff.
I see.
Well,
You're in a phase. You're right. I'm wrong. I guess I should remember these phase diagrams for water and steam or something. You can just be at a point where water and steam can coexist, I guess.
Anywhere along that.
You're along that line. Okay,
that's not a phase transition.
It's not a phase transition. You're right. You're along some lower dimensional surface where you can have phase coexistence.
Yeah, that's.
Okay. Yeah, no, not okay.
There is
coexistence or something. I mean.
Yeah, there is a coexistence of two phases separated by a boundary. But at some point we will consider, like at some part of this talk, I will consider like describing some particular configuration of these fluids for which I need a equation of state, and then for that case I will resort to this this specific setup anyway. But that's like at the end of the thing. But other than that,
you are
most of the
looking for
talk
stable lump or it's
stationary.
Stationary fluid configurations.
It's important to note that the behavior of the microscopic field theory at or near the surface can in general be quite different from that in the bulk. And this difference would be captured by new surface transport coefficients in the effective theory. And some of these transport coefficients may just suggest there are new relations between the bulk transport coefficients, or some of them might be just particular to the existence of the fluid surface and might not have nothing to do with the bulk transport coefficients, which will anyway be there even if there is no surface. A well-known example of such a surface phenomena at the leading order in derivative expansion is surface tension, which is well studied. And here we will study the surface transport coefficients at the subleading order. We will in one more derivative expansion, but we will recover the physics of surface tension also.
So it's analog of surface tension, but maybe dissipative.
And importantly, the surface transport coefficients carry entirely new information about the microscopics and modify the fluid equations at the surface very non-trivially. Like one example is just looking at the effective theory, we cannot say how is surface tension depending on the temperature. For that we need to look for more than effective field theory, and we might need information from microscopics, and new transport coefficients might be important in those situations, as we will see.
And I'm really sorry because I'm sure you will come to this, but just to ask the question anyway. Usually fluid mechanics is valid as an effective field theory when things are varying slowly compared to some mean free path or something.
Yeah.
Now, when you have a surface,
Drastic change.
In the approximation where the surface is very thin, there's a drastic change, right? And so, you will come. Sorry.
And one central simplifying assumptions in our work is that we will be considering stationary fluid configuration, and for stationary space-filling relativistic fluids, by which is analogous to saying that it has no surface. The constitutive relations for the stress tensor and the currents and equations of motions could be significantly constrained from a simple physical criterion, which is that the symmetry currents, including the stress tensor or other currents to other global symmetries, follow from an equilibrium partition function. It was work done by Siraj, Jyotirmay, Shantani, and Navamita and all. The stationary fluid configurations are considered in the presence of non-trivial background fields, like the metric and the gauge fields corresponding to other conserved charges. And we will consider this equilibrium partition function is written as functional of this background fields. That will be the main idea, and I will roughly say what are these, and I can come to the details later. These background fields are slowly varying, and they serve as sources in the relativistic fluid equations. So in relativistic fluid equations, we have on one side the fluid variables like the fluid velocity or the fluid temperature, and the fluid relations relate them to this relate them through these fluid equations to the background fields, which are like sources. And now we can substitute the solution of these fluid variables in terms of the sources like the background fields, and we can put them back in the putative action for stationary configurations, and then we will obtain this equilibrium partition function as a functional of those background fields. The fluid equations and the solutions in fluid fields are constructed in a derivative expansion. Therefore, the partition function can also be expanded in a derivative expansion in terms of these background fields and their derivatives.
Usually a partition function involves integrating over something.
Over the microscopics coming down from the microscopics in that sense?
Well, that's my question. It sounded here like you started with classical equations of motion. You solved solution in the background of sources, and then you plug that solution back into the classical equation of motion. So there's no integrating over anything in that.
Okay. So in some sense, what I'm saying is, I'm trying to give a picture in what sense this partition function can be like. What is the how to look at it in terms of basically at the very first go, I will write the partition function or action, whatever I have in terms of the fluid variables. So I'm just trying to motivate it, like how can we think about it to be written, this partition function to be written as a function of the background field.
So that I understand this. But the partition function implies integrating over something.
But like when writing down this partition function, we will allow for like all possible symmetry allowed terms which are like can be constructed out of these background fields and all. So in that sense, I think it will capture the information of integrity.
Sorry, I realized I misunderstood. Because there's no action, there's no Lagrangian.
I'm saying if there is an action,
But the action is for
in the microscopic theory. Yeah. Then like one can integrate out from that and come down to this effective theory, or like one can write down an effective action at the level of this effective theory, and then I can think about this partition function to be written in terms of the background field.
How can you write down an action for something that includes dissipation?
Okay.
This is without the dissipation.
So it's partition function.
Sorry, go ahead.
No. It's important that you're dealing with just stationary configuration. Where I think those terms are not at play.
But there are recent developments like where
So I can ask you really simple. What is the action a function of?
The action.
When you say the word action,
I didn't mean to be any formal thing by the action. Like I'm just trying to say, I can write down a partition function at the level of like thermal partition function of quantum field theory on a stationary background.
Okay.
And which is like
that's microscopic.
That's okay. And then possibly I shouldn't say this can be actionless. I was just trying to motivate it like. I can think of it like that, but whether that action can be written or what are the complications about it, I'm
not asking anything technical. My question is, pretend I'm a real idiot. That's the level of the question. So the action is for fluid variables or for microscopic variables?
The fluid variables.
Fluid variables.
So what's an ideal? That means it's an ideal fluid. Is that?
Stationary.
Stationary.
So I think the fact that it's stationary allows him to sort of not include any dissipated terms.
So usually for an action, I would use it to solve equations of motion. But this action, I'm not allowed to do that because stuff can't move. Is that? So,
or rather, you would get those. My understanding, where you should have correctly, you would get those solutions correctly out where the fluid is stationary. Because then, if you had the full Navier-Stokes with the dissipation terms, you're not going to have any contribution from the dissipation terms anyway, and you correctly incorporated the contribution.
So I can write down an action for a fluid, and I use it just to compute equilibrium solution in the presence of sources, and nothing else.
I think that's my understanding, but I think maybe it will become clear. It will be very explicit. Right? Maybe we come back now.
So you're saying you do that also for this surface?
That will be the goal of this.
So like
write down a thermal partition function where I have this surface, and if there are extra terms that I can write down in the partition function for the actual or what will be the structure of the partition function. But once I've written the partition function, I'm like which is argued from symmetry considerations or possible. Then I can follow there and come to
the surface tension is different only for static solutions or also steady state solutions?
Whenever there is a stationary lump of fluid, there's a force balance equation at the surface, and I can say that there's something which is not allowing this bulk of the fluid to just spill out or whatever. I'm using it in that sense. So once I've got the partition function, the symmetry currents from the partition function can be obtained by varying it with respect to the background fields. this symmetry current so obtained can then be compared with that which is expressed in terms of the fluid variables to the constitutive relations. So when I'm writing I can take a completely, I can bypass the, I'm not think about the partition function and can write down the constitutive relations for the fluids like the stress tensor or the symmetry, other symmetry currents in terms of the fluid variables. And then I can compare these two things, like the currents that I have obtained from the partition function, and with that which I can write down in terms of constitutive relations. And this comparison will not only express the fluid variables in terms of the background fields specific to the stationary configurations under consideration, but also will provide non-trivial relations between those transport coefficients, as we will see.
So that's the thing. You were saying that this partition function is such that you can apply the Noether prescription to get T mu, the stress tensor
and the
charge.
Won't that just depend on some functionals? I mean, say you take the action as some zeroth order plus some corrections to the actions. So that say Z1 plus Z2, Z2 is the correction that you are talking about. So that, when you compute all the stress tensor, that will be a function of this.
Yeah, and I will write down the partition function once and for all, and I will see what are the extra information that has gone in that, writing in that, and I write down equations of like this, following this.
But that's the same story as T mu in its expression in terms of the fluid variables. That also has this coefficient.
So that's okay. I mean that the zeroth order will be something like P by T. I mean the pressure by T, not the equilibrium temperature. So you can compare
the other constants. Then these other constants can be compared with the constants appearing in the constitutive relation.
So in this course, one of our principal goal will be to adopt such a method to constrain transport properties at the surface of the relativistic fluids. So the plan is introduction, which I have already done with. I will describe the basic setup, and then I will consider perfect fluids at zeroth order of derivatives and see what are the surface effects. Then I will consider next to leading order corrections, first order for uncharged fluids to the surface. And later I will come back to some fluid configurations, specific fluid configurations in 2+1 dimensions, where this surface tension will be varying as a function of the temperature, and then I will finish with some conclusions and so the basic setup. So I'm considering a relativistic fluid living in a space-time which is this curly end, and if you pick a time-like Killing vector which has the most general stationary metric like this. And there are three functions: sigma, ai, and gij. And I may also need some global charges, given charges, for which I will use this curly a's. Since none of the functions depend on time for our stationary assumptions, all the quantities of interest, including the conserved currents, can be dimensionally reduced on the time circle, whose radius we will take to be T0, and this reduced language will be very it's possible to use that reduced language because of this stationary assumption for most of the discussions relating to the partition function and things following from that. So upon reduction on the time circle, I can see from the metric, I can reduce on the direction t. I can get I will see that there are gauge fields. There will be kk gauge fields, which are denoted by these AIs, small AIs, and the manifold which I get by reducing on T will be denoted by n with a subscript s. This is the full manifold after reduction, and the time translation invariance will survive as a gauge invariance corresponding to the Kaluza-Klein gauge fields. And all our constructions starting from the partition function must be manifestly invariant under this Kaluza-Klein base transformation of small AIs, and along with the diffeomorphism invariances that I have in other coordinates in the NS, which are XIs. It's also convenient to define a new set of shifted gauge fields. Well, while we will mostly not work with any charged transports here, but since we are taking considering a language of this reduced language, it will be so we may move from this curly A's to the capital A's or the normal is whatever it is, which are like manifestly invariant under the KK. It can be shown that this is.
Could you just go back and remind me what's little AI? It's
So this is
okay, it's the GT. Yes. Thank you.
We can use some gauge field AI. So the set of background fields, the background data as this function sigma, small ai's, gi's. If I have gauge fields, I can use this zero component of the gauge field and the spatial components and also the time circle.
Sorry,
Please go ahead.
just sorry. Sigma was then
The e to the power sigma.
in terms of time. Okay, good.
Sigma. Nothing is different.
What's special about the capital A's versus the curly A's?
The curly A's are like the U1 gauge fields,
I understand.
and but they transform non-trivially under the KK transformation. So I can build these straight A's, which can be shown that are invariant under the KK transformation. So, like if I write something in terms of AI's, that is manifestly KK gauge.
In other words, under the T goes to
Under
T
the
plus
time reparameterization.
epsilon X, then AI also changes.
AI also changes. So there is a compensating thing between these.
I'm sure it does.
Yeah, okay. We can.
And T naught was what? That
For
is
the time circle.
asymptotic size of the time circle.
Right. And now we want to describe a lump of relativistic fluid. So we will assume that the fluid is confined to a submanifold N of. Sorry. This will be N. Sorry, it's okay. It's a submanifold of N, which is denoted by M. And the fluid surface is considered to be a codimension 1 hypersurface, which is denoted by f of x equals to 0, some relation. And the region inside f of x equals to 0 is that capital curly M, which can again be reduced from the time circle to obtain like this subscripted M. In fact, fx can be taken to be a spatial coordinate itself, which is positive inside the fluid and negative outside. And okay, I've already said this MS is also a submanifold of the MS with a compact boundary. And now I have this normal vector which is orthogonal to the fluid surface, and I can define it like this, normalized, like that. Yeah. Now the partition function. The partition function.
Oh, it's stationary, so that's why f is independent.
So the partition function, after performing the trivial time integral reduction, can be schematically written as this. So is as a function of, let's say, the background fields, the derivatives, the theta function, which has the information of the surface, and its derivatives.
Sorry, so can I ask again? I don't really understand what this object is.
This S.
Yes. No, the W.
That is a log of the partition function.
So I don't know what you mean by partition function. Sorry, it's the same question I was asking. Can I give you two options of what you mean by partition function? You can tell me which one is right. Okay. So one possibility is you start with a partition function for a quantum field theory with microscopic degrees of freedom on this background, and you integrate over all fields. Okay. The other option is, and I don't quite know what I'm going to say here. You write down an action, classical action for for fluid variables, and I'm told that such an action makes sense as long as nothing moves in time. You just use it to solve equilibrium configurations. You solve those solutions, and then you just plug them back into the action. So there's no integrating over in that last one. It's more like a Hamilton-Jacobi function of the partition.
It's definitely not the first one.
It's not the first.
It's not the first.
Okay, right.
But
yeah, if I remember what Shiraz and Shantini and Loga and these people did was to invent an action functional like that in terms of the fluid variables, which gave the correct form of T mu nu, and that's to say you do some Noether variation of this, and that gave you the correct stress tensor and the correct. What do I mean by correct? It gave you a T mu nu as stress tensor, and it gave you the charge currents.
this is now the action which involves fluid variables and metric.
That's right. But it still has the symmetries of space-time translation and the charge rotation, etc. So you can again construct some T mu nu and the charge current.
T mu nu only on stationary configurations. So
this gives you some T mu nu. Okay, this is parameterized by some unknown coefficients.
This S or the S that included
the invented S. The invented S, which includes various powers and derivatives of the fluid velocity, okay, and the temperature field. Okay. Now you find out the stress tensor from there and the charge current from there. And here now this T mu nu guys, of course, will be as some series in the fluid velocity and the derivatives of the fluid velocity, derivatives and powers of the fluid velocities with some unknown coefficients which are inherited from the unknown coefficients in the action. Right? Now there was this demand.
Constitutive relations.
So good, but the constitutive relations were even more, even wider. Okay, because they included possibilities that the second law of thermodynamics might be valid. Now, what they showed is that on the constraint where the second law of thermodynamics was exactly saturated, I mean, this del mu J mu of the divergence of the entropy current was exact. No, from here I don't know how well Loga now in his new formalism has an entropy current also in this double stuff. But what they found is that these parameters that come from this action formulation are the ones on which satisfy del mu, J mu. I mean, the second law of thermodynamics inequality is saturated. Okay. So this is a smaller set of parameters compared to the most general set of parameters that the constitutive relations could have. Just by counting, you can show that if you write an action formulation and if you write an arbitrary T mu nu, okay, then somehow you have more, okay, in the constitutive relations, and the reduction is precisely by demanding that del mu, the second law of entropy is divergenceless, and that is precisely where also all the dissipative terms disappear. Okay, so that's the kind of, I'm saying perhaps this is a little vaguely, and the fact that such an action formulation might exist was not clear. So it was only after they wrote down, by trial and error, something like that, and they found that all the equilibrium configurations that they had earlier found, okay, without an action formulation, can now be found as solutions of this action formulation. This is the kind of thing that I seem to remember.
Just to ask you, I think this may help. First of all, I think instead of using the word partition function, what for all purposes, because you're doing completely classical physics, we can say free energy. Which is a good thermodynamic concept, right?
Yes.
So I think at zeroth order, please correct me, what you're saying is, all right, suppose we have the fluid in a gravitational field. Now it's at rest, I want to understand the free energy. Let's assume there's some way to calculate it. As a functional or function or whatever of the metric, then varying that answer gives me the stress energy tensor.
And the stress energy tensor including the TT and IT components?
Yeah, because you can vary G mu nu.
So you sigma and the AI and so on.
Okay. And so they say, well, this is a way to compute T mu. Take the free energy for the fluid, after subjecting it to some background metric field, vary the metric field, and the response of the free energy gives me T response. Now, just the fact that it's coming out like that gives some consistency conditions that you will tell us, but I think that's the rough. They posit that there's a free energy, which in the presence of sources, which gives us the correct stress energy in response of the system. And then they start from there, something like that. But maybe what would help, and you might come to it, is if you did it for the simplest case, no boundary or something, if you can take 5 minutes, uncharged fluid and tell us how
I
you
have.
Fantastic. Thank you.
So correctly saying this is the free energy in a classical setup. This depends on these kind of variables, this functional, background fields, the derivatives, and theta functions and derivatives. So theta function is a distribution function of the surface function fx, and it's introduced to encode the variation of the fluid fields at the surface, and it contains all the information of the surface. For example, like you were saying, like the validity of the fluid approximations and all. In principle, this theta can depend on the width of the surface, and width of the surface in the sense the dimensionless quantity that I can build out of the width of the surface with the temperature circle. But we leave all that implicit in our description.
Theta is not the Heaviside.
In a limit, it will be a Heaviside theta function.
But more
generally, it's a distribution function, and it's non-universal. Like it depends on the fluid how it will be.
So you're saying an example of the theta would be exponential of minus f square over 2
something like that. And like this will be the fluid surface, and depending on the width of the fluid surface and the temperature at which I am working, I can consider this theta to be a strict Heaviside theta function, while its derivative will be like strict delta function.
So its derivative is the delta, the equation of the surface.
Right.
Okay, right.
So this theta function is purposely used to indicate the fact that in the limiting case where the parameter, so the parameter is missing, but it's like the width of the surface, like the dimensionless number of the number that I can construct out of the width of the surface with the another scale that I have is the T naught, temperature scale. And in that approximation, we can have a theta function, step function.
So f of x is like a step function, yes.
F of x is like a theta function. No, f of x is a condition that the fluid is there. Theta of f, like if the fluid resides within f of x, z equals to 0, it's the bulk of the fluid. And beyond f of x equals to 0, there's like the vacuum, or the different phase, or the other phase. So the theta function that should determine the boundary is theta of fx. Like that will put the constraint that if f of x equals to 0, I am at the surface.
So f of x is something like a shape function that you take of the surface. Some shape function.
Yeah, f of x is the equation of the surface. So now we can expand this A's in a derivative expansion, keeping in mind the reparameterization invariance of the surface, and this can be schematically written like this. So I have a staff which is multiplied by this theta function, and a staff which is proportional to the derivative of the theta function. So if I forget the second line, the first line was what, like all these terms inside, they corresponds to like this lower index says how many derivatives on the background fields are there. Like if it's 1, there is one derivative on the background fields. At most, one derivative on the background fields and all. So that first line corresponds to the space filling fluids when there is no surface. And the effect of the surface is encoded in the second line where I have a derivative on the theta function. So these objects are like terms in the bulk of the fluid, where I have 0 here. The upper index signifies how many derivatives on the theta are there. So these are the terms in the bulk of the fluid and are exactly the ones that have been considered for space filling fluids. Okay, so and like I can do a by parts integration here, and I can write down this partition function like this. Sorry,
with a pointer.
Oh yeah. And so I can write down the free energy of partition functions like that. But I have a piece which is like the surface, so in the bulk of the fluid, and I have a piece denoted by this delta function which is at the boundary.
So you are not writing any contribution from the phase that is sitting outside, because that's deconfined and that's lower order in large n counting.
Yeah.
That's
So
the
n square is within, and for a specific setup that I have that in mind.
This is an expansion in number of derivatives in theta.
there are two kind of derivatives. So I have like put the derivative on the theta as a different status than the normal hydrodynamic derivative. So I have like theta, derivative on theta, high derivatives on theta, each of which is multiplied by something which contains the normal derivation of theta, normal derivation in fluid dynamics.
So the higher derivatives in theta look like they're becoming more singular and therefore more important.
So, but I mean, we will work up to this order, but like all higher derivatives on theta, you can do a by parts and bring those derivatives on n and other stuffs here, and like we'll have effectively this form.
Is there any unique decomposition into which order of derivatives?
Which order of derivatives on theta?
Is there a unique way of specifying that if you can do integration by parts?
This is the surface, right? So by parts will introduce some surface.
That's exactly what this Nilay are. These are the extrinsic curvature of the surface. You mean like how to? I mean, I can just count how many derivatives on the thetas are. Like if it is a delta function, this is like a delta function, or it's a delta prime.
And the delta prime, you said you can do an integration by parts and turn it into a delta.
Turn it into a delta, but then there will be other terms like all the like there will be like this will be modified.
Yeah.
So I can say that I'm working to this order, like some order, and I will write all possible terms which are like built out of these terms. In that way, I can like incorporate that.
You know, there is the usual difficulty in hydrodynamics of describing shock runs. So that's the kind of stuff that Sandeep and David are worried about. So you have some you have some surface which is somewhat like a shock front because in that direction things are changing. So what is exactly the trick that you have which is allowing you to
Write it in this way?
bypass that difficulty?
So I'm saying the variation, like there will be a variation along the surface for the fluid fields for sure.
Along the surface is fine. That
Across
can
the
be
surface.
Across the surface. Yeah.
Across the surface.
Yeah. So those are large derivatives.
Those are large derivatives, but like large compared to the like there the thing will come that I have a like theta function like that. So if I'm like so this thickness is large or small compared to the temperature I'm working relative to that scale.
So you're going to say this thickness you are going to take much larger than the thermal wave.
Thermal wave.
So it's large in length compared to the mean free path or thermal wavelength, but small compared to something. Qualify as a surface or not.
I mean,
is there another bound on it in terms of?
Other than that, like it can be of the. I mean, it's so we keep it implicit because like it's not universal. Like there are fluid configurations where this might change, like and like that. But what I'm saying is this approximation is justified. Like the fluid dynamical approximation because the fluid surfaces also vary over this thickness, and this thickness is like compared to the.
So there is a phase boundary and the transition region is bigger in size compared to the thermal wavelength, and then you're doing a derivative expansion in inverse powers of the thermal wavelength.
Should this region be smaller compared to characteristic size of the bulk?
There is no restriction.
So that's what I was wondering. Now, should it be that then you're thinking of fluid flows where things are varying on some length scale, which is much bigger than the thermal wavelength, and the surface thickness is in between.
In between, yeah.
Is that what you have in mind? So that because otherwise, in what sense is it a surface?
In what sense it's a surface? Yeah. Yeah. I'm sorry. So that other restriction is like what puts like this like a status of surface.
But is there a parametric separation between these scales? I mean, the surface thickness, thermal wavelength, and the typical bulk, length scale. Why? How is the surface different from the inside the bulk of this confined unit? How did it work for this plasma ball solution?
Plasma ball solutions of Sierra, they had like a similar construction of writing it with features.
I mean, it's clear when you are doing the expansion that things are parametrically suppressed in the width of the surface compared to the temperature. Right? Because that is suppressing the high order. I guess what is not clear is whether there is a similar expansion going on in terms of the size of the surface compared to the scale at which the fluid
things are varying.
Maybe you will encounter that as you go along.
Yeah. So these extra terms are like extrinsic curvature of all the derivatives on the n, which are extrinsic curvature of the surface.
Now, when you transfer derivatives from theta function to the n, you say they become extrinsic curvature.
Yeah.
Only if these derivatives are along the surface. So extrinsic curvature is defined on how the normal changes around the surface.
You can project.
So, but if this derivative is across the surface, then it's not extrinsic. It's how the normal changes across the surface. If you transfer the derivative. And if the derivative is how theta changes across the surface, if you transfer it on the n, it's not an extrinsic curvature.
So we will work in an approximation where I'm like considering these thetas to be like the variation of theta has nothing to do with along the in the normal direction to the surface or not.
It's n dot del theta. Right?
N dot del theta. This is because just like this is because of the reparameterization invariance of the surface. Like you can take f goes to some other function times f, and like okay. First of all, you have to use something as a scalar here, so you have to dot it with something, and so this is a scalar like that. And this f, this specific combination is used because this is invariant under reparameterization of f. Again, reparameterize surface equation.
Probably along the surface, theta doesn't vary. Does it?
Along the surface.
So the only variation of theta is probably normal, right?
That's taken care of by this.
But what I'm saying is, suppose you were doing a gradient expansion of basically the effects related to the surface. Then you start with theta of f, then you add the next term, which is the derivative. But the only derivative which is non-zero is the normal.
End of thing.
And so this is in the standard way in which we do the derivative expansion of fluid mechanics, but here only the normal terms. Then I don't know, at the second derivative level, something is right? That's what you're saying.
But he's saying that he's transferring the derivatives from theta to n. He can interchangeably keep the derivative from theta or n. He said that, right? You keep the integration by parts.
You can think it like that, but here let's say this term. This is like 1 means there is only one derivative on the theta, and this one is like there is only one derivative on the background.
You can say that, but at zeroth order, what you have is a double expansion going on, where you are expanding at the rate in which the fluid, at the rate in which things are varying compared to the temperature, and also at the rate at which things are varying across the surface, right? And that double expansion, the first term in the expansion where things are varying across the surface is theta of f. The second term would be gradients of theta, but there's only, my understanding, one non-trivial gradient, which is n dot theta. Right? Now, since it's a double expansion, every term in the expansion where things are varying with respect to theta are then expanded in terms of how things are varying in the bulk compared to the temperature. So the theta f term is expanded in a gradient expansion like that. And then the del theta terms are further expanded.
If I include a further term like n mu into del mu del u.
That would be the next step.
Won't that be more fast varying than the other?
No, so my understanding is that the idea is that the n dot del theta term is suppressed compared to the theta term because they are taking the surface to be wide compared to the temperature. See, The reason why the viscosity term is suppressed compared to the leading term is because the velocities are small compared to temperature. Right? In the same way here, they're taking the surface to have a width which is in length bigger than the thermal term. That's why it is suppressed. Right? Is that right?
So that for here, like here, the idea is if I just look at any one of these blocks, there is a expansion in terms of the regular hydrodynamic expansion, but like variations are large compared to the implicit scale of the time scale or mean scale. There is another one which is like this, and that and on the thetas, and which is also justified because I'm taking the surface accordingly compared to that.
Is that a good approximation for, say, water in a glass?
I'm not sure. But I mean, okay. So there, the surface of the fluid is like forced, and
but by your G mu, literally.
I think David's saying you understand, you take a glass of water,
yes,
in the gravitational field, it fills up the glass to some extent, then you have air or whatever, and in that case, it's this, how thick is the boundary?
I've not thought about that.
Or a droplet in a space station.
So once I write down the partition function in that expansion, I can vary the partition function with respect to the background metric using some Euler principles, and we can get the stress tensor, which will also have a similar expansion like theta and then T million, 1, 0, 1 and 2 like that. Also, we are able to remove the derivatives of the delta function in the partition function by integration by parts. So derivatives are still present here. Like this is not within some integral, and this they have to be.
Read the last one. Derivative which is the delta function. You mean theta of its derivative is defined to be delta? So this comes to your question. Is that right? You can always remove. So then I'm confused. You mean a term which involves a derivative on theta can be traded for a term which involves theta with the additional derivative on the derivative? That mixes the orders of your expansion. Then I'm confused what the expansion is. I thought usually there's double expansion, then you have two small parameters, just to make everything well defined. So let's say that you have two small parameters. One is, let me say you have two large parameters. One is the rate at which, the length scale over which things are varying in the bulk compared to the thermal wavelength, and the other is the width of the surface compared to the thermal wavelength. So now if you have two large parameters, you do a expansion in terms of their inverses with two independent small parameters. Then it's justified. If you can trade one for the other, then I don't know, it's not valid.
I think I have to say it correctly.
So that means the zero tolerance stress tensor will now be modified because of this extra pieces. What?
I will come to that. Like how. So whatever it is, like you write these things here and you derive it, like differentiate it with respect to the background fields, and you get whatever it is. But like the thing is that in T mu also there will be a structure like this. So some theta, derivative on theta. So there is a special role played by the function fx in the partition function or the free energy. It's like if I take this and differentiate it with respect to the f, extremize the free energy with respect to f, I get back the equation like the equation of motion for fx derived by extremizing the partition function with respect to it is the one which determines the location of the surface, and this is identical to the particular surface fluid equation which follows by demanding diffeomorphism invariances in directions orthogonal to the surface. Like conservation of the stress tensor dotted with the normal. That equation is like the equation of the that comes from demanding diffeomorphism invariance in directions normal to the surface, and that appears to be the same if you derive vary this partition function with respect to f and obtain an equation. And these are like intermediate constant known as the Young-Laplace equations. So
actually I don't quite understand that. So you think, suppose I think of f itself as a dynamical variable, then you're saying that I take equation of motion with respect to f. Okay. And then what do I get? I mean, let's just from the first term.
So you will have you will get a term just from here, which is like delta of f times del mu also. Here, this is like, so if you like do this, you might get a term which is like del f on theta f times, let's say, del mu of it. This is like the n mu, and this is like the delta function. And and then there will be other terms which are there like that. So this is delta f fixed at f equals to 0. So this is a surface equation. This equation I'm saying here by putting it equals to 0 gives me the same equation if I like start from that partition function or differentiate it with respect to the, let's say, metric, or like metric meaning I have all these components of the stress tensor and AI. So I get T mu nu, I do mu T mu nu.
By diffeomorphism invariance, you mean conservation of stress.
Or yeah. So I'm saying this equation is this equation. Dotted. And this is some in the literature it's called Young-Laplace.
Is the location of the surface something dynamical to be decided? So can you give me an example? We have some three-dimensional manifold, and somehow as you're varying the metric, the location of the surface is changing. That seems very.
Or like you perturb the fluid a little, and there is deformations in the surface.
I'm only allowed to do equilibrium, you told me, right?
Okay.
So I have to change the background matter.
The background matter.
The surface changes.
Yeah.
What fixes the volume of the fluid?
Like once the equation of the surface is fixed, it naturally like fixes the volume, right? It contains within.
So for a given metric, are there many possible solutions to the surface?
Yeah. I'll come to that in the later. There are like different configurations which can have these solutions. There will be a phase fraction for them.
Sorry, what are S naught, S01, S02? Are those how are those position dependent?
No, they are not position dependent, but they, like I'm saying, they are functions of the background fields and their derivatives. But this equation, when you follow this route, compute the stress tensor, which is like basically a diffeomorphism invariance. Like conservation of stress tensor is like a diffeomorphism invariance you have in it. So it contains the, like it's not that AS directly depends on the positions or whatever. It's written as a function of the background fields. But when you derive the stress tensor equation, this is a statement of the diffeomorphism invariance of the surface. And I'm saying if you take this and find out the equation of motion of F by varying, and you will get the same equation. This is the Young-Laplace, called the Young-Laplace.
So I'm also bothered by the question that David asked. I mean, it's like for raindrops, there is a unique shape. So I mean, so are you saying that they can have various shapes depending on the numerical parameters that appear in the action?
Parameters.
Once you
The
keep
thermodynamic
some set of
parameters.
numerical parameters in the action,
There will be a unique ones chosen. Like these balls and rings, like of the cirrus and this too. So these are allowed solutions, like with different topologies. But once you fix that which energy or which angular momentum or this rotating thing you look at, there will be one which will be favored compared to that.
I don't know. My question, which I thought David was asking, but please correct me, is you again take water, and you fill it up to some level. How far up you go depends on how much water you put in, right? So when you have two phases, don't you have to specify something about which can coexist? Don't you have to specify something for example, the chemical potentials or something which tell you how much of one phase you have. Was that? I'm not sure if that's what you were asking.
I think it was just something similar, but if there are many solutions to F for a fixed fixed gravitational field, no, that's exactly what you want. There's many possibilities, and somehow it must be matching. I don't know about chemical potential. Maybe chemical potential or pressure. Usually for this Maxwell construction, that's what you have to do.
Pressure, but isn't there something more? Because I could have water going up to some extent, or more.
That should be determined by the gravitation, the solution for a given gravitational field. So for Geltam's example, if you take a raindrop in space, it's purely spherical. If you put a raindrop on Earth, it's a raindrop shape.
But can't you have raindrops of various sizes?
Assuming that the total amount of water, of course there is also this limiting thing. Given the surface tension, I mean, if it is any larger than that critical thing, it will just split.
And it can't be any smaller either. So there's just a unique size, isn't it?
I mean, there is a critical size. It can be smaller than that.
It can be smaller.
Yeah.
And stationary. Okay, go ahead. You're saying you get unique, given pressure, temperature, whatever parameters, you'll get unique solutions. With some maybe you'll get some discrete set of solutions. Right. Just to tell you, since you're still in basic setup, and Arunava told me that at 11:30 we have to vacate the room. So you have to type it accordingly.
We should go to
So now, from the other side, like forgetting about the partition function, I can just write down a stress tensor. Also, in a it's like the constitutive relations in terms of all possible terms that I can have from symmetry with restrictions or unequal restrictions, like that I denote with this C. So this partition function gives me a stress tensor which is P, and I can, based on like symmetry considerations and has a structure on constraints of the structures, I can write down it. And the transport coefficients are the functions of the scalar fluid fields that multiply specific symmetry structures when this T tilde mu mu 0 or 1 is further expanded in a derivative expansion. Now comparing this stress tensor with these stress tensors, like one of them from here, like written like this, and from the partition function gives us non-trivial constraints, and this exercise, when executed for the fluid configurations with the surface, not only gives relations among surface transport, but also related them to some of the bulk. So there are some issues of the frame choice, but the frame choice that we want is like the fluid doesn't spill out of the surface. So I need a condition like that to be imposed, and then like the normal like Landau frame, which indicates the fluid is an eigenvector of the full stress tensor, is not a good choice, because now the stress tensor will have contributions from the surface. So the fluid variables like will, and also I want like the fluid variables. The fluid variables has to be continuous. Like if I take the bulk fluid velocity and at surface, it should not like jump. So there should be a continuity in those equations, in those velocities. So Landau frame for the full stress tensor will not be a good choice, because that will not allow the velocity to be continuous. But a possibility is to work with the a Landau frame kind of condition just for the bulk part. Then what I'm saying is at the surface, the fluid is not moving along the directions of the energy flow. But that's well. I mean, there is nothing wrong in that. What I just want is like the fluid variable at the bulk, it becomes continuous, something continuous at the surface, and so we make that as a part of our frame fixing conditions. So we fix frame and make it sure to up to all order that this is true, and this is true even at the leading order. But when it gets ahead of the corrections, there is a possible way to maintain that. And for the directions orthogonal to the n mu, like along the surface, I can put some conditions like this to take care of the whole thing.
So now perfect fluid at 0th order, where I will see all these things are working. So the partition function can be written like that, which is P as a functional over on those variables, and these are the definitions of the stress tensors. I should vary with respect to the background fields. I get
Sorry, what?
sorry,
What
sorry.
is W? I only ever ask the same question. T subscript 0, what is that?
T subscript 0 is like the temperature, the radius of the thermal circle related to that, and like in patches, I can define a locally rate-shifted temperature, which is like this T0 to the minus sigma.
So I was expecting to see something written. Oh no, I was expecting to see something written as a function of temperature and velocity, but you've solved for those already and plugged those
Background fields. So this W, this free energy is written in terms of as a function of the background fields.
T0 wasn't one of the background.
Yeah,
fields. It was. I thought it was sigma and G and little
Sigma G little a for gauge fields, capital A naught, capital AI, and T naught. Like
That was you started with the metric, but there was an identification.
T0 was just the periods.
periods.
And just to say, when you write log Z or F or W, whatever, then free energy, then what you're just postulating this formula, right? You're saying diffeomorphism invariance in the spatial directions means it should be root G, that is the three-dimensional metric, times a scalar, and the scalar you choose to write in terms of these variables.
And also have to maintain the KK.
And the fact that T0 and e to the sigma come in this combination is simply that you could choose to move some of the periodicity of T0 into the variable sigma. So that fixes that combination. And then whatever remaining scalar is there, you call it P. It will turn out to be the pressure because we know this is the free energy, but you call it for now. Okay, good.
So now if I evaluate it explicitly, I get like just from these expressions, and now I can write down the T mu mu like for a perfect fluid, like this. And if I compare them, I get like this. This P is this P, capital P. This curly P comes from there. This is identified with the pressure. Energy density is this quantity, which is like this is the entropy, and all. Velocities come out to be like this, and the temperature T is.
And let me ask you something. Presumably you have not included any additional gauge field here, otherwise they could be other scalars.
Yes.
So, but your little AI, which you would have got from the metric, that could be there.
That could be there.
So you've not written a possible scalar term coming from there.
But you cannot write any possible right term respecting this diffeomorphism and KK variables at 0th order of variable.
And at 0th order.
That's
Which means
perfect.
no spatial gradient. Okay, so then with that, this is the only term.
So now with the surface, I should write down something similar here. Like the C will be something on the light pressure on the surface. I can obtain the stress tensors and can like compare with the stress tensor that I can write down, which will have a surface part, and the surface part can be like this is like something chi and chi, the surface energy, and this chi will turn out to be the surface tension, and this, and if I compare them, I obtain these equations, right? Which is like so. These two equations can be written like this, and this chi is the surface entropy, which is like the derivative. It's like the derivative of the.
What is chi E?
Chi E is defined like this, which comes with this.
So these are all terms only on the surface, involving the velocity, or this, what is mu?
Oh, sorry. This is the projector, which projects orthogonal to both mu and mu.
Chi is C. What is C?
C is that one.
I see.
This is like the pressure.
So you could write down two quantities in the stress tensor you find there, like in the bulk case, they're determined by one.
It's like the
Presumably that's known by standard thermodynamics.
thermodynamics. Now, one should look to this factor, chi E. This is the surface entropy, or which comes because of the temperature dependence of the surface tension. So, if surface tension depends non-trivially on the fluid temperature, which means I have some degrees of freedom at the extra degrees of freedom at the surface. So the surface entropy is non-zero. And
so sorry, chi is the surface tension, C or whatever.
Yeah.
So this T temperature field, when did you introduce that? I mean, there is of course this T naught.
Yeah, so T naught e to the minus sigma is like the red sigma.
That's what you call it.
Yeah.
All right.
So now if one computes the stress tensors like that, so the bulk part of this equation, which is like this, is just like the conservation equation. And at the surface, it will have two components. So one can like project it along the surface and can consider normal to the surface. Along the surface, for like the perfect fluid, it just gives 0. And but the interesting one is the equation, which is conservation surface stress tensor conservation equation projected along the normal, which comes out like this. And this is like the it's called the Young-Laplace equation. And if I assume that like this chi or the surface tension doesn't depend on temperature, then the thermodynamic relation says chi e is minus chi. So that term goes away. That extra term, which is like the modification due to the surface, and I get back the standard Young-Laplace equation. But if there are like degrees of freedom in the surface, there will be like extra contributions to the Young-Laplace equation, and we see the first signature of the surface effects coming into play in equation.
So K is the extrinsic.
K is the extrinsic trace of the extrinsic curvature.
And this nice formula that the pressure is equal to surface tension times K. That also sounds like that's a very standard thing.
Standard thing. It's like sigma over R for.
If you include your correction term from the entropy, surface entropy,
Yeah, so
that's also just very standard. You've reproduced it.
Yeah, it reproduced.
The fact that you get the same equation by varying f, that we should be able to understand just from, again, the coordinate invariance, right, or diffeomorphism invariance, because that is the underlying reason for here. So you change some coordinates and you get a new f in the new coordinates, but etc. etc.
Now for superfluids, like okay, and there is an extra entity which is like the superfluid velocity. So in my zeroth order stress tensor, I have to write an extra quantity, like the currents will be modified like that, and the partition function has to be written like this bulk part and the surface part, but they will depend on the norm of the superfluid velocity. And now I have a gauge field, extra gauge fields, and like this thing. And finally, the equation of motion is the surface.
Sorry, I'm really sorry. I should really shut up because you're running out of time. But before we go to superfluids, just this generalization you have, where you have extra terms if you have degrees of freedom on the surface that contribute to entropy. I suppose this must be known in the literature. But aren't you finding some, run by me a little quickly, are you finding something non-trivial there by thinking in terms of the partition function? Because in general, were there two parameters which got related or not? Just in the zeroth order, that is, you had chi, and then you got chi e in addition. Can you go back one more transparency? I just need to digest this. I'm sorry, one sorry. So, in general, if I knew nothing and I tried to write down T1 mu nu, I might have written chi e and chi as totally independent. And now what you're telling me is that no, chi e is actually related to chi, at least in terms of d chi dt.
Yeah. So if chi is 0, then that extra term is not there.
No, I understand. But if it's there, then it's not something random. It's related to d chi dt. And that's something which came out of the partition function.
Partition function, right?
Or could you have obtained it?
No, so the partition, so the surface tension, depending on the temperature, gives an extra contribution to the Young-Laplace equation.
Namely to chi e or to chi. I don't know what.
Or like the.
But let me just ask you this: you have two coefficients here,
Yeah.
right? If I knew nothing and I was doing a derivative expansion, I would have said they are independent of each other.
I'm getting a relation.
You're getting a relation between them, right? Was that relation known? Or is it new? That is it somewhat non-trivial and coming out of the analysis from a partition function? Or is it some well-known thing, if you thought more conventionally, that you could also get to?
You might need extra constraints on it. You need extra,
So
like the
conservation, but how would conservation of energy? It wouldn't give you.
Can I ask the same question about the bulk? The bulk is P minus. And the bulk have the same properties, right?
same as
and one was P pressure and the other one was entropy, and there's a relationship between the two, which is entropy is P by dt. Is that the right? Probably in some.
yeah.
And of course that's not a new relation. That's just standard thermodynamics. And the same must be true of
The same
Must be true.
Yeah, this is probably just, this is of course standard thermodynamics and probably some extent. Okay. I'm just trying to understand what the partition function, approach is. Maybe at the next derivative.
Exactly. Okay. Because the Young-Laplace equation is nothing but a statement that you have some restricted general coordinate transformation which retains the surface. Because you don't allow general coordinate transformations which keeps violates the surface condition.
Okay. Sorry. No.
Yeah. So for the superfluids, actually, there's an extra contribution here. I mean, that actually stays. Even if you say that there are no extra degrees of freedom in the surface, that will kill this term. But this term is there, and it will be interesting to understand that. I don't think there is good understanding of this term in the superfluid.
Okay. The size, the superfluid velocity. Okay. Yes.
So now, like, this was leading order at the zeroth order derivative, but if we do like next to leading order with a surface, and so we start with the zeroth order partition function, and so we start with the zeroth order partition function. For first corrections, we need to write down all Kp, Kjmp and scalar terms at higher ordering derivatives. The bulk of the fluid does not receive any corrections at first order, which is like known, which is a statement that you cannot write any scalar respecting the symmetries at the first order. But at the surface, we have an extra entity which is the n mu. So we can write 2 parity even and 1 parity odd quantity on the surface stress tensor. And then therefore the surface will get these extra 3 transport coefficients. But this is not complete, because like if you have a second order term here, that will contribute to this. That will contribute because on a surface by part that is like a first order term. So you have to write down also the second order terms at the bulk. So these are the second order terms which are built up. So now you see that this f, small f is del I aj, and these terms are there. So this is the full partition function that's constructed like this. So this part is the bulk, this is the boundary. I have like 3 extra. So these 3 terms were known, P1, P2, P3, or from the bulk analysis of Shiraz and all. And now you see these 3 extra. And you follow the same procedure. You find out the stress tensor. It will have 2 parts. One is like the surface, the bulk thing and the surface thing. And the explicit forms of them are like this. It's not very important. You can also satisfy the conservation equation, which is explicitly checked along the take the 2 components along the surface.
Sorry for the paper is not going to take the class.
Okay, we don't have a proper fabulous fit.
Except by exhaustion.
So this is
total constraints.
So this is the current that flows from the partition function, which follows from. So now we have 3 extra. Yeah. So I have like P1, P2, P3 in the bulk. These are like the bulk second order transport coefficients, and these are like surface transport coefficients which we expect to be coming new. Yeah. that. The stress tensor which follows from the partition function is like that, and I'm writing just the surface part because the bulk part will be what was done for the bulk stress tensor at second order. And now we can you start writing down the surface stress. So we want to classify find relations between the surface transport coefficients. So we write down the surface tensor in equilibrium, classifying all terms allowed by symmetries. And then we reduce the stress tensor along the time circle, go to the reduced language and compare it with the one that follows from the partition function. Now, the frame choice that we have chosen only fixes the bulk stress tensor. Because once I have used all the two, like the n mu, q mu at the surface equals to 0 and the Landau-like condition for the perpendicular to fluid, I fixed my u, so I cannot u at the surface extra. So I cannot. So basically, the stress tensor at the surface is not constrained by frame, the frame choice. So we have to write down all possible terms that are allowed by symmetries at first order, without imposing any restrictions. And that happens to be like that. So there are like 4 scalars. So these delta primes means I'm at the surface. There are 4 scalars which you can write down at first order of derivative and satisfying the kk gauge invariance and the diffeomorphism invariance. There are 7 vectors and there is 1 tensor which you can write down at the first order of derivative in the surface. And then you should write down the surface stress tensor with all those 7, all possible terms like that.
So now this is what you have called T mu of 1.
T mu 1 following from the constitutive division, not the partition.
I see, that's what you're doing now.
So I will compare them to get relations. And as you can see, here are a lot more coefficients. This set in these equations, they are like the transport coefficients which sit with these possible terms which I have written earlier. So I can count, there are like 31 transport coefficients here.
So you mean at the next to leading order, where in the bulk normally with rotational invariance, etc., you just get the shear and bulk viscosity. Here you get 31
at the surface.
Okay. That's quite a lot.
But we know that in the partition function analysis we had 3. So we should expect 28 relations when we compare them. And like they come
after imposing the second law, I mean the divergence.
No. This stress tensor, surface stress tensor is without any restrictions. That's what I said because I fixed my frame for the bulk stress tensor. The surface stress tensor is free. I have to write down all possible terms which are allowed by.
So out of this 31, only 3 are independent.
3 are independent.
But by demanding what? Okay, let's see.
I mean, that's quite striking. Just by demanding that the free energy is a scalar and its variation with respect to the external metric is the stress tensor. You see very huge.
So on this side, on the non-partition function analysis kind of side, there from 31 to 3 you would have gotten by demanding that the entropy current is divergence, right? That is my understanding. That is to say that there is.
I mean, okay, that analysis we have not done. I mean, from entropy,
okay,
but it should be.
So you will now relate this 31 guys to the
partition
just 3 such parameters appearing from the partition.
Oh, I see. Just to understand, sorry, I'm only slowly catching on. Had you not known about the partition function story, but you just took this stress energy tensor and in addition said there should be entropy current and then demanded
divergence less,
or at least always greater than equal.
If it is always greater than or equal to 0, then it gives you some inequalities, etc. That gives you some reduction, and
gives an inequality.
That gives you an inequality, and then no, that is probably enough. That is probably enough. That that I don't remember. Whether it is the positiveness of the divergence, of the entropy current, that is enough, or you have to actually saturate it. Okay.
I think it's an equality type constraints.
Yeah. Then it gets reduced from 31 to 3.
Should.
In the bulk case, whatever those numbers are.
Yeah.
And though that number then matches with the
Partition.
number of parameters that appears in the partition.
That was a
analysis.
bulk analysis.
Yeah.
Okay, so that's one way where you have to think about entropy current. Here your point is that
Just partition function from
these
there.
anyway don't involve, these must all not involve dissipation. I mean, this is another thing that's confusing me. How could you possibly get constraints on dissipative coefficients by doing stationary, by just thinking of stationary fluids?
What's more, I think the constraints include things like the viscosity.
They do?
And on your next slide, those equations seem to relate.
Okay, but then it is strange. Is it
Can you put up those equations?
The
Yeah.
stationary solution should not constrain this. That's dissipative cost. I mean, the equilibrium partition function.
It should not. Yeah. So maybe these are not dissipated. Is it that many of these? Go ahead. Many of these are not
Were
dissipated.
these constraints known before?
These constraints?
Were these relations?
These relations? No.
The
Because the surface effect, this is not.
the fluid mechanics people didn't know.
I don't think so.
Can they measure these transport coefficients?
The ones that we are doing, they're not. But I don't know from the fluid community.
Yeah. I mean, they must not be dissipated.
I think
I
that's
was kind of missing something.
I can't read off where are you reading of
I think I was
the.
wrong, it doesn't look like this. Are the zetas? Zeta 2 and zeta
These are
3?
bulk transport coefficients.
But dissipative transport coefficients?
I think
Viscosities. At first order, it's only viscosities, right? I think.
so. For the bulk, there are no connections at first order.
But you have to go to second order.
Second order.
These are second order. I'm sorry.
Oh, I see.
Okay.
So you don't have the bulk and shear viscosities because they're dissipative and they don't appear in your.
Yeah. So maybe these are second order.
Second order.
coefficients which
Because
are
this is
non-dissipated.
bulk coefficients are second order.
Okay. Maybe that's how
I see. So this has constraints on non-dissipative transport coefficients, also derived by insisting entropy current is conserved.
Interesting. Okay.
So by comparing the previous stress tensor with the stress tensor that's coming out here, you can derive. I mean, you can see actually there are 28 relations here, and this shows that the linear response to the particular deformation of the surface is intimately related to some otherwise unrelated transport coefficients, second order transport coefficients in the bulk.
By the way, just an aside, since we have the thing I was confused about, the other thing, let me just say, which is how much water there is. Of course, if you're doing a relativistic fluid, then that's just number density, right? Carry on or something. I mean, if you were doing non-relativistic, then there would be an additional equation of conservation of mass or something. Then
The zeroth order equation one has to impose.
Yeah. I mean, no mass conservation or something. Otherwise, here it's just you to specify some concept. So,
Sorry, you can have relativistic fluids without conservation, where it's just
yeah, but then
antiparticle pairs.
right, and then there would be no way to say how far up the water goes. You know what I mean? There'd just be at some temperature you just have a plasma, and it would.
I see, and then the volume's fixed, right?
Yeah. Sorry, confused. Go ahead.
Yeah. So again, now for the perfect fluids, we saw that if there is non-zero surface entropy or the surface tension is varying with respect to the temperature, there are extra terms which come into the normal component of the stress tensor conservation. So now we will try to see how does it so we were to work out some explicit constructions of these fluid configurations and try to see if we can see something there. So we now consider a few simple stationary fluid configurations to demonstrate the relevance of a non-zero surface entropy. As discussed earlier, the fluid equations, in particular the Young-Laplace equation, gets modified when there is a non-zero surface entropy, or equivalently a non-trivial dependence of surface tension on temperature. And we work out some particular solutions to these equations and explore the consequences of a non-zero surface entropy on the phase diagram of this fluid configuration. And we will be focused on perfect fluids in 2+1 dimensions, including possible high density corrections. So we are at the 0th level of derivation. And for working out explicit configurations, we need the knowledge of the equation of state. So we have to consider a specific system, and for that we use n equal to 4 Young-Laplace theory, t equal to 4 dimensions, compactified down to 2+1 on a Surfsworth cycle, which is done by like Siraj, Toby, and all. They are dual to rotating black holes and black rings in Surfsworth compactified ADS5 by the CFT correspondence, and we basically revisit the analysis in this paper by Shubhanil, Lahiri, and Siraj. So they constructed the solutions to the relativistic fluid equations that describe the long wavelength collective dynamics of the deconfined plasma phase of n equal to 4 Young-Laplace theory, compactified down to n equal to 3 on a Surfsworth circle. These solutions are stationary, axially symmetric, spinning balls, and rings of plasma. So these are spinning plasma balls or spinning plasma rings.
The purpose of going on in one direction is just to take everything translationally invariant in that direction.
So one has to take this one of the circle to be periodic, which is the Surfsworth circle, and that caps off at the IRS.
That's in the bound. Right?
That's in the bound.
But in the boundary, the reason to consider these particular configurations is just you're making them simpler and just having them axially symmetric.
Okay. If you were simulating like a thermal circle, there is automatically Surfsworth, right?
But you don't want that one more extra. Like
no, wait. So you are going to.
So I'm.
You're going to 2 plus. Oh, yeah, I'm sorry. You have a space which is a Surfsworth circle, and then you will also.
So now there is a the confinement deconfinement transition is like when these two radiuses are the same. The critical temperature is when the radius solidon goes to black hole.
Yeah.
One of them is the confined and another one is the
Yeah.
So here to have both phases coexist, that's what you like, right?
Yeah.
So you mean you have some region, I mean both of them are stable for this, the only parameter.
There's a like the confined phase, the confined has a decay which is like the degree of freedom is like order n square and order 1 outside. So the decay over the time is there, but at a large n limit, this is like the metastatic configuration. So they studied the phase space of such solutions. I mean, spinning balls, plasma balls, and rings of plasma. And one of the key assumptions was that the surface tension was constant throughout the surface. Constant over temperature, which we would like to relax. Because we want to see the effect of that extra term, which is equivalent saying that we want to consider surface entropy to be non-zero. This was assumed mainly because the value of the surface tension for the interface between the confined and deconfined phase of n equal to 4 Young-Laplace is known only at the critical temperature. The full dependence on the surface tension on temperature for this interface is still unknown, but we would like to parameterize this ignorance in a suitable way and study its consequences.
I mean, I wish Raz was here, but I thought they just found solution.
They found solutions.
They found bulk solutions.
They found no, but these are like the spinning lumps of fluid, like Shubhanil and Siraj that work was done.
But I mean, did they make an assumption, or did they just say, okay, you have two circles and one of them is
I thought they made a bulk analysis. This is how do you find such things? Just like their original solution.
Exactly.
So, I think it was
were they making? I thought they were just solving Einstein's equations.
No, but they were studying fluid equations. Like
I don't know what they did as well. So you say
Oh, this is
what they actually did was they studied fluid solution. But there was this earlier paper
is Toby offered.
where they studied just the
the plasma balls.
But here they studied lumps.
Yeah, that was static.
This
Toby,
is also
this is a spinning plasma rings and spinning balls and
stationary solutions. Okay, where they take surface tension constant. Okay, I'm with you. Thank you.
So this dependence is still not known for the spinning balls and rings, but we want to parameterize this ignorance. So the configurations have the feature that the temperature is constant throughout the surface. Also, there is an empirical fact that the surface tensions must decrease with increase in temperature, which follows.
How do you know the temperature is constant? Don't you have to solve it?
Yeah. And so we start with this assumption and then we say that this is something. We show that this is something. So there is an empirical fact that the surface tension must decrease with the increase in temperature, which follows from the fact the surface temperature will be otherwise. So
the surface is now a circle, so everything is happening in the xy plane.
Yeah. So, assuming that the surface temperature is very near to the phase transition temperature, we can consider the following dependence of the surface tension on temperature. Just considering these two. So that I'm parameterizing the ignorance by this kappa. So if you put kappa equals to 0, this chi naught is the constant surface tension that's shown in this later paper, assume. But we are trying to say that I can have this is a possible temperature dependence. So one needs to do, I don't know, systematic microscopics and all to get that, but this is a possible thing to start with. So kappa is the parameter that parameterizes this ignorance of the exact temperature dependence of the surface tensions. And then,
sorry, why do you have that constant term at all? I mean, shouldn't
no, at T equal to Tc it should reduce to the critical temperature value.
Sorry, this is the first one.
So the bulk fluid equations are not affected by this kappa, and the solution in the bulk remains identical. At the inner and the outer surfaces for the rings, which are denoted by subscript minus and plus respectively, the Young-Laplace equation or alternatively the stress tensor conservation equation along the normal direction comes out to be like this. So if I forget this kappa terms, this is what they gave. This is like the chi times k, the extrinsic curvature thing. But now I get a modification like this, where omega is like the angular momentum they have, r plus minus r like the two radiuses of the. This is like an annulus, so there's an outer radius and an inner radius, r plus and r minus. So for the rotating balls, when I don't have an inner surface, and therefore no condition associated with the minus there, it's just like at outer surface. So this is the modification that will happen to the Young-Laplace equation due to this kappa. The phase diagram that emerges out of the analysis is significantly modified by the introduction of kappa. And so the phase diagram that they studied was like this: entropy versus the angular momentum for a fixed energy. And so this black line is for the ball. So like I think it's not visible, but for kappa equals to 0, this black line goes straight and touches at entropy equals to 0 at some angular momentum. And this is the small ring, which again starts somewhere here and goes to here, and this is the large ring, which again goes here, and all of them touches like this thing. So there is a phase transition there, which was there for kappa equals to 0, from the fat ring to the plasma, the spinning ball, spinning fat ring to the spinning ball. Now if you introduce kappa, they all get terminated well above.